Alright, it's time to do number 17 on that same worksheet. And here we go. What is the pH when 200 mils of 0.05 molar LiOH lithium hydroxide is added to 200 mils of 0.05 molar methylamine bromide? Okay, methylamine bromide is a salt. When it dissolves, we're going to end up with methylamine, which is a weak acid, as discussed in problem number 15. The thing we have to keep in mind with this particular problem is that now we unfortunately can't oversimplify things with using the HA plus water yields, this is an arrow, yields H3O plus and that other thing, A minus. We can't oversimplify our problem with this particular simplification this time, because now we're adding some strong base to our solution and we have a little bit more to worry about than what we did before. So since we're adding strong base, this particular reaction is not necessarily our best option of what to use. What we're going to use instead will be one where we have a hydroxide come into play so that we can include this LiOH in our problem, which means we're going to be looking instead at our BH plus, which is this, as discussed in problem 15, BH plus hydroxide in equilibrium with water and our conjugate base. Okay, this is the same exact reaction, but this one is taking the point of view of hydroxide ions, which we have to do because we are specifically adding hydroxide ions. Okay, and we know that it's okay to do this because our equilibrium concentrations of hydronium and conjugate base are very, very small compared to our starting concentrations of acid and hydroxide, which we know from the problem we just did. Problem number 15 told us that at equilibrium we have 2.23 times 10 to the negative 5 molar conjugate base and hydronium, and that is more than 3 orders of magnitude away from the concentration of both species that I'm starting with here in this problem. So I can definitely not have to worry about either of these two species for my new problem, and I can just start off talking about BH plus and OH minus as if there is no conjugate base in solution, not worrying about the protons in solution, and keeping in mind that water is going to be a pure liquid and not included in my equilibrium constant expression that I'm going to make from this rice table. Okay, so here's my rice table. Here's the reaction I've chosen. My starting concentration of BH plus is something that I have to think about for a moment here. I started with 200 mils of 0.05 molar CH3NH3Br. So that's 200 mils of 0.05 molar CH3NH3, but I also have to keep in mind that my new solution is going to have not 200 mils, but 400 mils. So I need to make sure that I start with an initial concentration that is consistent with my new volume, which means I need to figure out how many moles are in my solution so I can divide it by the total volume that I now have to get my molarity. And to find this molarity, I need to find my total number of liters and my total number of moles. How do I find those? I know that moles are equal to molarity times volume, because that's the same thing as moles over liters times liters. The liters cancel out, they leave me with moles. Okay. And my total volume down here is just going to be the sum of the two parts of the solution that I'm adding up. Okay. So to overall calculate my new solution, I'm going to do molarity times starting volume, my starting molarity and my starting volume, all divided by my new total volume. Okay, so for BH plus, for methylamine, what I'm talking about here is molarity of 0.05 times a volume of 0.2 liters divided by 200 mils plus 200 mils is 400 mils, which is 0.4 liters. Okay, and that number is going to be the same for BH plus and for OH minus, because I'm adding the same amount and same molarity of each of them. Okay, so when I calculate that out, 0.05 times, ooh, I just dropped my marker, hang on. Okay, when I calculate that out, 0.05 times 0.2 over 0.4, I'm going to get 0.025 molar, and that's going to be the same starting concentration for both my hydroxide and my BH plus, my methylamine. So the first thing that we have to recognize at this point is that we have a solution here with a strong base, OH minus. And in solution, OH minus is going to completely neutralize. It will steal whatever protons it can from the nearest species it can find, which in our case is going to be our weak acid right here. All of our hydroxide is going to neutralize for as much weak acid as we have, which, since we have equal amounts right here, means that all of our hydroxide is going to neutralize with all of our weak acid, and we're going to be left with 0 of both of these and 0.025 of our weak base. So now we have to remember that since we have officially taken care of all of our strong base, we're going to have a new equilibrium be reached, because this is in equilibrium. We've taken out all of our strong base, which means that we've pushed our equilibrium over to this side. But now that our equilibrium is so heavy to this side, it's going to get pushed back over to the left. We're going to see another shift to the left following Le Chatelier's principle. Okay, so I'm going to rewrite this whole thing as now we're starting with our base again, reacting with water to form our conjugate weak acid and our hydroxide ion. Okay, and I know I'm starting this equilibrium with 0.025 molar of my base, an amount of water that doesn't matter, and 0 of my weak acid and my hydroxide ions. I'm going to lose some unknown amount of weak base and gain an unknown amount of hydroxide ions, so that I end up with 0.025 minus x, x, and x for each species. Earlier in the worksheet, we were told that Kb for this is equal to 10 to the negative 6th. And so 10 to the negative 6th. Yeah, okay. So Kb equals 10 to the negative 6. And we know that from our equilibrium constant expression, this is equal to BH plus times our hydroxide ions divided by our weak base. So 10 to the negative 6 is equal to x squared over 0.025 minus x. Is this x negligible? Is 0.025 more than 3 orders of magnitude less than 10 to the negative 6? This is 2.5 times 10 to the negative 2. That's a difference of 4 orders of magnitude, or 10 to the 4th. So this is significantly less than our k value, enough that we can call this x negligible. Okay. This should actually be a greater than sign if I'd been paying attention. Sorry, you thought I was saying that I loved you. Ha! Anyway, moving right along. I'm going to move down here. 10 to the negative 6 then is equal to x squared over 0.025. If we multiply both sides by 0.025, then we end up with x squared is equal to 2.5 times 10 to the negative 8, I believe. 1, 2, 3, 4, 5, 6, 7, yeah, 8. Counting zeros, fun. Okay. 10 to the negative 8. Square root of both sides gives us that x is equal to 1.5 times 10 to the negative 4, or 1.58 times 10 to the negative 4. This x is equal to my concentration of my weak acid as well as my concentration of my hydroxides at equilibrium. There should be another equal sign here. Okay, so if I want to find POH, that's the negative log of 1.58 times 10 to the negative 4, which is 3.80, and pH plus POH equals 14. So my pH is 14 minus 3.80, which is about 10.2, which is what Dr. Laude's key says. So good job, team.